Assalamu alaikum students, I am Saida. Today we will start physics and we will start with chapter number 10. It is about simple harmonic motion and waves. It's my first lecture on this chapter. Let's start. First of all, we will see what is simple harmonic motion and we will see the examples also. Simple harmonic motion is a kind of vibratory motion. And what is a vibratory motion? In the vibratory motion, a body moves to and fro or back and forth about a point, and this point is obviously the mean position of the body or the resting position of the body. Let's see the examples of simple harmonic motion. The motion of mass attached to a spring on a horizontal frictionless surface. The motion of a ball placed in a bowl. And third, the motion of a bob attached to a string, and this system is called as pendulum. So the motion of pendulum is also simple harmonic. Let's see the definition of simple harmonic motion. Simple harmonic motion occurs when the net force acting on a body is directly proportional to the displacement of the body from the mean position and is always directed towards the mean position. Let's see the characteristics of simple harmonic motion. The bodies which execute simple harmonic motion, they show these characteristics. Number one, a body executes simple harmonic motion always vibrates about a fixed position, and this fixed position is obviously the mean position or resting position of the body. Number two, its acceleration is always directed towards mean position. Number three, the magnitude of acceleration is always directly proportional to its displacement from the mean position. A is 0 at mean position and maximum at extreme position. And fourth point, its velocity is maximum at mean position and 0 at the extreme position. So these are the characteristics of simple harmonic motion. Let's study a body which is attached to a spring, and let's see the motion of this body and prove that whether it is having a simple harmonic motion or not. Before studying that situation, let's see the conditions for simple harmonic motion executed by a mass which is attached to a spring. First condition is the vibratory system must be frictionless. So friction should not be there in the system. Second, the vibrating system must obey Hooke's law. Hooke's law, which you have studied in class 9th. And fourth, the system must have elastic restoring force. And fourth, the system must have inertia. Let's see the motion of mass attached to a spring. Let's prove that mass attached to a spring shows simple harmonic motion. First of all, we will suppose a situation. Consider a mass which is attached to one end of a spring and the other end of the spring is attached to a fixed support. The mass is moving on a horizontal frictionless surface. The mean position of the mass is O, which is the resting position. The spring is stretched to point A by a force F. Look at the diagram. We are discussing the first figure, which is indicated as A. Now let's see the derivation now. If the spring is stretched to point A through displacement x, a restoring force F appears in the spring. Then what happens? Then according to Hooke's law, this force is directly proportional to the extension in the spring. Therefore, F directly proportional to x, and F would be equal to Kx. What is K here? K is spring constant and its value is equal to F over x. So spring constant indicates stiffness of the spring. If the value of K increases, the stiffness of the spring also increases. And if it decreases, then the stiffness or the value of K would decrease. The restoring force which appears in the spring will pull the body back to its mean position O. Therefore, F would be equal to minus kx. As we have seen that whenever we whenever we pull the body to point A, extension in the spring would occur. And due to this extension, a restoring force would develop in the spring which will pull the body back to its mean position. Therefore, F is indicated with the negative sign. F is equal to minus kx. Here negative sign indicates that restoring force is pulling the body back to the mean position. And according to the second law of motion, we know that F is equal to ma. This is the equation of second law of motion. If we put the value of F in equation 1, we get ma is equal to minus kx. By rearranging this equation 2, we get A is equal to minus k over m x. Here k over m is constant. What is k? K is the spring constant. What is m? M is mass. So k and m both are constant values. Therefore, we can, if we eliminate these two quantities from the equation, we will get A directly proportional to minus x. This equation shows that acceleration produced in the mass attached to a spring is directly proportional to displacement from the mean position. The negative sign shows direction of acceleration towards mean position. So when the body comes back to the mean position, it would not stop here. Why? Because due to inertia. And what is inertia? You have studied in 9th. Inertia is the property of a body due to which it tries to maintain its state, whether it is the state of rest or the state of motion. So, due to inertia, any body can maintain its state of rest or motion. As we know that the body is moving, it is coming from the extreme position A to the mean position. It is in motion, therefore it would continue its state of motion. So it would not stop at its mean position O, and it will move to the next extreme position, which is on the left side, indicated as B. So when it is moving towards B, what happens? The spring compresses now, and the restoring force will develop again in the spring. It will pull the body back to its mean position O. This way the body continues to vibrate about its mean position, and all the time A would be directly proportional to minus x. Let's see the explanation of the motion of the body which is attached to the spring, which we have just seen. Let's see. The body vibrates about mean position, which is the first point of simple harmonic motion. So it is fulfilling the first point. The second, the restoring force produces acceleration in the body, as we have seen in the example. As the restoring force is directed towards mean position O, therefore acceleration is also directed towards mean position. So this is the second thing which is fulfilled by the body, this body attached to a spring. And the third point, magnitude of acceleration increases as displacement of the body increases from the mean position. A directly proportional to minus x. If the value of x increases, the value of A would also increase. Okay. So the acceleration, the value of acceleration is maximum at extreme positions A and B, but it would be 0 at mean position. This is the third point of simple harmonic motion which is fulfilled here in this example. Fourth point, as the body moves from O to extreme positions, velocity decreases and becomes 0 at extreme positions. Why does it decrease? It decreases due to the restoring force. The restoring force will try the body to bring it back to mean position. Therefore, as it goes from mean position to extreme position, the velocity would decrease due to the restoring force. The value of velocity increases as the body moves towards mean position, and it becomes maximum at position O. So, girls, you have seen that all these 4 points have been fulfilled by a body which is attached to a spring. So, it is verified that motion of a body attached to a spring is simple harmonic. Let's see the home task now. I have given these 3 questions. First is define simple harmonic motion. Write its characteristics. Second, what conditions are needed for simple harmonic motion? And third, prove that horizontal mass spring system executes simple harmonic motion. The third question is long question, but first 2 questions are short questions. I hope you have understood the topic and you can very easily attempt all these questions. Do all these questions in your copies and send me the images. Thank you very much. Allah Hafiz.